Let's talk about a secret language. Seriously, it's a language made of numbers and symbols that's hidden all around us, and it can help you do some pretty amazing things. You can use it to plan a budget, figure out how fast something is moving, or, and this is a good one, figure out how to get on that dream spring break trip. Today, we're going to see how a few simple rules of what are called linear equations can unlock some really powerful stories. So, you might be wondering, okay, but how does this actually work in the real world? Well, we're going to follow a student named Caroline who's trying to save up for a vacation. And believe it or not, her entire plan can be mapped out with one single, kind of beautiful equation. By the time we're done here, you'll know exactly how to solve it. Okay, here's the deal. Caroline needs to save $2,500. Not a small amount. She's already got $400 saved up, which is a great start, and her part-time job pays her $15 an hour. So this line you see on the graph, that's her savings growing over time. The big question is, exactly how many hours does she have to work to hit that magic number? Let's build the toolkit we need to find out. First things first, before we can start solving anything, we all have to agree on the basic rules of the road. In math, we call this the order of operations. You can think of it like grammar. It's a set of rules that makes sure that no matter who you are or where you are, when you look at a math problem, you get the exact same correct answer every time. The rules are actually pretty simple, and you might have heard the acronym PEMDAS before. Here's how it works. First, you handle anything inside parentheses or brackets, always working from the inside out. Next up, you simplify any exponents. After that, you scan from left to right and do all the multiplication and division. And finally, you do one last sweep from left to right for all the addition and subtraction. That's it. Let's see this in action, because it really does prevent total chaos. With a problem like this, the key is to dive into the very middle, to the innermost parentheses first. Once that's done, we can handle the exponents. Now, notice this part. We do the multiplication before any addition. By following this strict order, parentheses, exponents, multiplication, then addition, we just untangle the problem step by step until we're left with one solid answer, 13. Anyone who follows the rules gets to 13. Okay, so we've got our grammar rules down. Now we can get to the real heart of algebra, solving for an unknown. This is where we get to be detectives. We're looking for a missing piece of information, and it's usually represented by a letter, like X, or in this case, W. Now, the most important rule in all of algebra is the idea of balance. Just picture a perfectly balanced scale. That equal sign, that's the pivot point right in the middle. If you decide to add 5 pounds to the left side, you've got to add 5 pounds to the right side to keep it from tipping over, right? Well, it's the exact same for subtracting, multiplying, or dividing. This one single idea, it's the key to everything. So it turns out there's a super reliable 4-step game plan that works for pretty much any linear equation. Step 1, clean things up. Simplify each side as much as you can using our order of operations. Step 2, use that balanced scale rule to get all the terms with a letter, the variable, over to one side of the equal sign. Step 3, do the same thing for the plain old numbers, moving them to the other side. And finally, step 4, do one last thing to get that variable all by itself. All right, let's take that game plan for a spin. First up, we simplify both sides, clean it up. Next, we use our balanced scale idea to get all the W terms on one side. Then we do the same thing for the numbers, gathering them on the opposite side. And for the final move, we just need to get W all alone, which tells us our answer. W is -1/2. See? It's just a repeatable process of tidying up until the mystery piece is all that's left. So far, we've been working with symbols and numbers, which can feel a little, abstract. But what if I told you that every single equation we've talked about so far is also a picture? It's time to move from pure algebra to the art of graphing. Just think about that for a second. All of that simplifying and solving and balancing we just did, what does it actually look like? The answer is one of the most basic, fundamental shapes in the entire world. And boom, here it is. Every linear equation, when you plot out all of its possible answers, draws a perfectly straight line. Each of these lines tells its own unique story. Some are really steep, some are almost flat, some climb up, others point down. And all of those characteristics are described by the numbers right there in the equation itself. So if every line is telling a story, then the main character of that story is something we call its slope. The slope basically defines the line's personality. It tells us exactly how steep it is and which direction it's headed. So what is slope, really? Well, it's just a simple ratio. We call it rise over run. All that means is, if you pick any 2 points on a line, the rise is how far you go up or down, and the run is how far you go side to side. The slope, which we usually call m, is just that rise divided by the run. It gives us one single number that perfectly sums up the line's steepness. Looking at this graph again, you can totally see it in action. A line with a positive slope travels uphill as you go from left to right. A line with a negative slope, well, it travels downhill. And the bigger the number is, whether it's positive or negative, the steeper that line is going to be. It's a crazy efficient way to describe how a line behaves. Okay, now that we kind of get a single line's personality through its slope, we can start looking at how different lines relate to each other. Because just like people, lines can have these special relationships, and you guessed it, it all comes down to their slopes. There are two big relationships we care about here. First, you've got parallel lines. Think of them like train tracks. They run right alongside each other forever and ever, but they never ever touch. Then you have perpendicular lines, which are the exact opposite. They crash right into each other, but they do it in a very specific way, forming a perfect 90-degree angle, just like the corner of a square. And here is the beautifully simple rule that runs the whole show. If two lines are parallel, their slopes are going to be exactly the same, identical. And if two lines are perpendicular, their slopes are what we call negative reciprocals. That's just a fancy way of saying you flip the fraction and you slap a negative sign on it. So if a line has a slope of 2, a line perpendicular to it is going to have a slope of -1/2. Simple as that. Okay, we did it. We've built our complete toolkit. We get the order of operations, we know how to solve for an unknown variable, and we can even see what these equations look like as lines. It's time. Let's go back to the beginning and solve our problem. Let's get Caroline on her spring break trip. All right, let's translate her story into algebra. Her goal, that $2,500, that goes on one side of our balance scale. On the other side, we have her earnings. That's $15 times some number of hours we don't know yet, we'll call it X, plus the $400 she already has in the bank. And there it is. 2,500 equals 15x plus 400. We have our equation. And now, we just unleash our toolkit. We use that balanced scale principle. First, we subtract the 400 from both sides to get the numbers together. Then for our final step, we divide by 15 to get x all by itself. And there it is. Carolyn needs to work exactly 140 hours. And if we go back and look at that very first graph, what do you know? That is the exact spot where her savings line crosses that $2,500 goal line. The algebra and the picture tell the exact same story. So what this all really shows us is that this isn't just about solving for x in a math book. This is a framework, a way of understanding the relationships between things, like hours worked and money saved, or time and distance, or cost and profit. A straight line is the simplest, most powerful way to describe change. So now that you can read this language, what kind of patterns and stories will you find in the world around you?